Okay, so this is a very vague figure of the engineering design process. Just basically the thought process. First, the definition. You have to define the problem. Right? So there's different tools to do that. One of them is called quality function deployment. That's what I'll talk about a little later on. And then the designer will go through the divergence, come up with brainstorming, conceptualize many different designs, and then transition, do the analysis, narrow those down to one or two, converge on one or two main designs, things that they want to try, and then they'll go through the prototype and testing. So they build the prototype, they'll think up some type of test for it, they'll judge the performance, and then they'll redesign. Based on that, they'll go back and make improvements and modifications. And like Nimrod said, it's a cycle. You can always redesign something, whether it's a chair or a phone, doesn't matter. Okay, so the problem definition stage, this is what happens first of all. We have to define the characteristics and the constraints of the problem. Artistic design, there are no constraints, there's no bounds, right? You can make whatever you want. Engineering design, we do have these constraints. One, science, right? Two, function, quality, of course, cost. So we have to work within these boundaries. Another thing, identify the customers. One, the end user who buys this. Two, who has to make it. So there's many different things to think about when designing something. And of course, the background research and benchmarking, what's out there, and helping you. Okay, so quality function deployment. This is a tool. You can use this in I have an Excel spreadsheet that will be on the portal website. You can use that to fill out the matrix. This is just a blurb about some of the things that can go wrong. You see to the left what the customer wanted is a tire swing, and then what marketing requested, and then some of the things that can go wrong. Okay. So why do we use QFD? To avoid those problems. Identify exactly what the design goals are and how they can be achieved, how they can be satisfied. So we take these customer requirements, things that the customer wants. Things like it has to be easy to use, it has to be comfortable, and we can turn that into engineering solutions, things that can be measured. Of course, it's a fresh eyes approach to the design. So say you have something that you need to redesign, like a chair or a phone. You have a mental picture of that, what it's going to look like. This is the way to shift that thinking from a form, what it looks like, to the functions that it has to do, what it has to do. And when you finish the QFD, the designer will use this to guide the design. So this is the structure. This will make more sense in a few minutes. We'll have your customer requirements. It's going to be a column. The row is going to be engineering specifications, and it's basically a matrix to correlate these and define our targets. The numbers got lost in translation. So the steps of the QFD, one, after determining who the customer is, determine the customer requirements, the relative importance of those requirements, convert those to engineering specifications, and then make the correlations, do the analysis to define and set the problem. And then set the targets and eventually go through the testing and improve the design with any modifications and different iterations of the design. Okay, so to show this, I'm going to use an example. Maybe some of you are familiar with the ball launcher, the catapult. So this was Family Science Night at Cahillo Elementary. It was the little bit younger group, the 5 to 10-year-olds. So we tried this out there. Not as technical as we're hoping with the middle school age group. You can see they did come up with some pretty interesting designs. One of them, they have different catapult designs. Can't really see here, but they have the They came up with different slingshot ideas. There's many different ways to do this. They found. Okay. And this is Matt working with the pressure vessels and the science behind that. So I was trying to get a close-up on more of these designs, but the kids kept getting in the way. This girl, you see here, she was in 2 of these photos. She really got into it and started adding things to it, and she got really creative with it. There was another kid that had one of the tubes was very popular. It had the tube and the rubber band and had the the kind of the barrel type thing. So he would go and he would test it, and then he figured out that he needed a guide for it. And so then he would go, he would test it, and he went back and put that on it, then he put a sight on it. So he was naturally going through this design process. He was making modifications naturally. And this is a natural process. We're just assigning different steps and terms to it. So this was the poster we had up. This was just a bullseye here, and they had to, once they made the thing with the simple materials on the table, they had to go and shoot at this, and the idea is to measure what kind of accuracy, see how accurate they can make this device. Okay, so first step, determine the customer requirements. For the ball launcher, a lot of this will be given. So these requirements are commonly expressed in qualitative terms. How it functions, size, appearance, cost, manufacturing. So this is what we want. This is what we want in the product. What we need to do. Okay. So for the ball launcher, what are some of the customer requirements for this? So this is a very simple QFD matrix. One has to be easy to use. The requirement we're defining in the project, or for the family science side, has to be accurate. See how accurate it can be. Of course, safety. That's always one. Can't hurt. Be safe. And then it has to be easy to make with the materials available on the table. Right? So these are some of the types of customer requirements. The list can go on and on. But this is, hopefully that will give you an idea of some of the customer requirements. Okay. Next step is to, which ones are more important? Just weighting. So in this scale, it's just 1 to 5 scale. So assign 5 is most important, so 1 is less important. This was what I came up with. Yours might be different. This is subjective and arbitrary, right? So I said safety first, then accurate, and then easy to use and easy to make. And so then it'll assign these relative weights. There's simple mathematical ways to do this. This is just a comparison chart. So you see the different requirements here. Easy to use, hit the target. Which one's more important? So you see the comparison here, 1, 0. One that's more important, assign it a 1, and do that for each one. So go through, and again, some of these might be different for you, but this is just what I filled in for that. And then add up how many 1s you got, and then divide that by 6. So that's just a simple way to do the relative importance of these. There's different ways to do it. Some of the list of some of the customer requirements, a little bit more expanded list. Just you have to brainstorm stuff for the ball launcher. Easy to use, accurate. Some of these are going to be rules. Can't throw or hit. Has to be quick to make. Has to use stored energy. What's the average distance from the center? How repeatable is it? Just some of the things that you can do in the class. Some of the tests that you can do. Very important step. Now we have to make engineering specifications. So for the example, the idea we've come up with is we give them the customer requirements, and then they make a prototype and test it. And then when they're doing their testing, you can come up with these engineering specifications. The main feature of this is that they're quantifiable. It's the stuff that we can measure, we can count. Every specification must have appropriate units. If it's not a unit, it's probably some type of customer requirement. Example, customer requirement is durable. What's an engineering specification? How can we quantify that? Yeah, how many times have you used it before it breaks, right? That's one. Average life to failure, so some examples down here. Fraction that survives over 10 years. So anything that you can measure to assign to durable. Okay, so this shows some of the engineering specifications. That's where you put those. Some of the things I came up with. How many steps does it take to use the ball launcher, the catapult? For the accuracy, let's measure the distance from the center. Those inches or the ring number on the bullseye target. And then inversely, for safety, what's the range of this thing? How fast is the ball moving? So the higher the range, the lower the safety. Right? So that's going to be an inverse relationship. For easy to make, number of pieces. How many pieces is in the ball launcher? Higher number of pieces, the harder it is to make. So after you come up with some specifications, you have to correlate these to your customer requirements. Right? So that's what this matrix is. So you can use different scales for this too. For this one, 9 is very related. 3 is somewhat related. 1 is weakly related. And if it's blank, there's no relation to that. So you can see the number of steps to use. There's a 9 here, so that's number of steps to use, ease of use. Those are going to be highly related. So that's how you do that. Everybody see that? So down here we have our targets. Steps to use, let's aim for 2 steps. Pull it back and let it go. So for the distance from the center, let's say 4 inches. Let's try to get within 4 inches. And then so on and so forth. Range 6 feet. So these are the targets that you're going to set for your specifications. We want to minimize or maximize this. Number of steps, we want to minimize that. We make that as low as possible. It turns out for all of these, we want to minimize it. We want to minimize the distance, the range for safety, and the number of pieces to make it easy to make. And the rest is in the Excel file. I'll go through the specification weights, and it will rank the importance of these. So it says number 1 is the range because of the safety. Right? So this is a way to analyze this problem. Okay, so sample list of some of the specifications, number of steps to make it, pieces to use, time to make, time to launch it. And these will all be correlated to the customer requirements. The trick is to come up with these tests, these quantifiable measures for your customer requirements. And after you practice, you go through this a few times, you'll start to get a hang of it. So I talked about this before. Correlate the customer requirements to engineering specifications. That's the center of the matrix. Set the engineering targets. This will be based on your experience. You have to guess at it. But then when you go to do some testing, you can go back and modify this later. Any of these customer requirements or weights or targets, it's a fluid document. You can go through and modify these as you go through the design process. You'll find that some of the targets aren't attainable. You don't need to change those. When we did it with the 5 to 10-year-olds, balls were flying off everywhere. We had to obviously have to change that. Okay, some comments. Always use QFD for the mechanical design. This is a way to change your thinking from a form or a shape that something's supposed to look like, decompose that into its different functions. What is it supposed to do?